record. Good morning. I almost forgot that I got you guys to watch the video, and I was just about to keep going and cover that material. So if I didn't say it to you, did you even hear me? So instead of doing that, I thought let's go through definitely one example in particular that I want to do, but also maybe we'll see if we can squeeze another example in. I'm all turned around with them changing the chapter numbers, so bear with me, but I posted some chapter 2, now chapter 3 practice, so I'll be stealing from those questions, and this was just now, so if you feel like, oh, I didn't stay on top of things and she posted stuff without me knowing. No, it was really just 5 minutes ago. So that's why, my apologies. But I also, it was like this morning, I was like, I promised to do all these things and I didn't do them. Because I've got, well, it doesn't concern you guys, but I've got another course that's really eating up a lot of my time. So you guys are like my fun course. And then there's Stat 240, which is like, yeah, it's a beast. But anyway, so I did post the formula sheet and the tables. Now the formula sheet is really just what I typically hand out. So if we were in person, right, this is what you would have on a test. And so you guys are working open book. And so of course you guys can have whatever you want, but this is a good starting point, right? If you kind of want to have a jumping off point, then you're good to start here. Notice that the chapter names, again, it's like I refer to the chapters, lesson learned, I guess. I shouldn't refer to the chapters, I should just call them by a name, because they'll change the chapter numbers on me and then I'm hooped. Everything refers to the chapter numbers. So anyways, just ignore the chapter numbers and you'll be safe. But so most likely, right, is the probability section that you'll be looking for, right? Those probability formulas just summarized, especially these conditional probabilities. I don't have a pointer on my webpage, but we're going to use that formula later. So let's see here. There's also the tables, which once we start talking about the normal distribution, we will sort of use the tables. I'm going to nudge you towards using some R code instead. But it's nice to have the tables because they're kind of old school, and that way you don't need to have software available, or you don't need to be working on a computer. So, but it's definitely old school, but it is how we teach it still, because a lot of calculators can't do these calculations, but a lot of them can anyways. So there's some tables. All right. I just noticed there's a news forum on here. I don't remember putting that there. It must have been by default. You can just ignore that. I'm going to delete that later. Guess I don't pay attention at all. So the chapter 2 practice, which is now chapter 3, very confusingly, I am going to bring it in, and it's that last question that I want to focus on in particular. So let me see here. Close that. Open here. Okay. Probability. I'll start now. Probability practice. Oops, that should say practice. How about that? chapter 3. Should change it to probability. Okay, so there are a few of these questions, but I mean, a lot of them are kind of a little bit too easy. The one I want, or not easy, but you can do them on your own, and I'll post the solutions to 2 and 3, but I think it was 2 and 3, but the one I really wanted to work through was question 4, which is on lactose intolerance, and it's a conditional probability. So that's why I wanted to focus on that, because that's the rest of that video. And conditional probabilities, they're kind of tricky, right? So they're difficult. Luckily, we don't rely on any of this later on. It's just one of those hurdles that we have to get through, and we have to say that we covered it, and then we're safe. So if this stuff doesn't jive, that's okay. We're gonna kind of parking lot it. It will come up on the final exam, but that's it. Okay, so it doesn't resurface for any of the other material. All right. But they are good skills to know. Let me just at 2:30, I think. I need lines, otherwise I'm all over the place. Okay. So we'll start with, good job watching that long video. I'll put long in brackets. It wasn't meant to be long, it just is. The long video. Okay. So for a little bit of review on conditional probabilities. So this is from the practice problems. It is so weird to me to think that we've already talked about this. I haven't, not this term. So anyways, so conditional probabilities. Oh, and I forgot to pop up the chat here. Yeah, lactose intolerance. Sorry, I missed that. Yeah, it affects everyone. Pretty much. So, so one thing to remember about conditional probabilities is that if we talk about generic events A and B, right, if we know that A has happened, then that could affect the outcome or the probability of event B, right? So one really common example is if you have a deck of cards and we're drawing cards without replacement, and I know that 3 red cards have already been drawn, right? Then that affects the probability of another red card, right? Because there are already 3 gone. So that would be a conditional probability. Whereas if you started out and you had a fresh deck of cards and you wanted to know the probability of a red card, well, half are red and half are black. And so then you know that it's 50% or 0.5, right? Whereas if you already know that 3 red cards have been drawn, right? Or 3 cards and all 3 of them were red, let me be specific, right? Then that affects the probability of the red cards, right? It lowers the probability of getting another red card, right? So those are conditional probabilities. So here's an example, and how the easiest way to solve conditional probabilities, in my opinion, is with a tree diagram. Okay, so what I want you to kind of get in the habit of is you're going to have some initial event, and that's your first set of branches. Okay. And then from that initial event, there's a second event, right? And so in this case, right, we're going to have, and I obviously stole this from a textbook, not because I love talking about race or anything. It's because it's a really good question. So just ignore that. And I don't know, if you think of something cooler to talk about, then that's great. But anyways, lactose intolerance. It's not that touchy of a subject. We're all lactose intolerant to some degree. So here we go. So lactose intolerance causes difficulty digesting dairy products that contain lactose or milk sugar. So it's particularly common among people of African and Asian ancestry. In the United States, ignoring other groups and people who consider themselves to belong to more than one race, can we just talk about how big of a chunk of the population we're removing, right? But we have to say that, right? Because we are ignoring that for this question, right? Then 82% of the population is white, 14% is Black, and 4% is Asian. We're assuming that those are the only categories. We know that's not true, right? So it's a very simplified question, okay? But so our first kind of event that has to happen is we need to know what race someone is out of these three possibilities, right? We're just focusing on these three. Then it says, moreover, 15% of whites, right? So now, if you are white, then 15% have lactose intolerance, right? 70% of Blacks, right? So that means that you have to be Black. And then if you are Black, then 70% of those people would be lactose intolerant, right? And 90% of Asians are lactose intolerant. So first question we want to know is what percent of the entire population is lactose intolerant? Okay. So if you look at regardless of race, and I guess regardless of race, then what percentage is lactose intolerant? Okay. Then we want to know what percent of people who are lactose intolerant are Asian. Okay. So let's see here. We want to start by drawing a tree diagram. You don't have to, but I find that it definitely makes it easier. Okay, so I'm going to solve this using a tree diagram. We don't need to. It's just a lot harder to visualize these probabilities without a tree diagram. Okay. But what we can do is we can list the probabilities that have been given, right? And so we're saying we're given the probability of being white is 0.82. Remember, we have to use the decimal version, even though we often talk in percentages. In our calculations, it's really important that we use decimals. So the probability of someone being white is 0.82. The probability of someone being Black is 0.14. And the probability of someone being Asian is 0.04. Right? We can add those up and make sure that they add to 1, but they do because we're assuming that those are the only categories, and that's weird, I know. So now, if we let L, so I didn't specify what these variables are, W, B, and A, because they're obvious, right? But now I'm going to let L denote lactose intolerance. Lactose intolerant. Okay. So then what we're told is that 15% of whites, so that means the probability of being lactose intolerant, given that the person is white, is 0.15. Okay. The probability of being lactose intolerant, given that the person is Black, is 0.7. And the probability of being lactose intolerant, given that the person is Asian, is 0.9. I like to throw the trailing 0 on there just to emphasize that I did 70 and 90. It doesn't matter. Obviously, trailing zeros don't do anything, but it just makes it look a little cleaner. That's just a side note. Okay, so you could work with these, right? And you could figure out, okay, if I want to know what percent of the entire population is lactose intolerant, what are you trying to find? You're just trying to find the probability of L, right? Without these conditional probabilities or anything like that. But it's hard to visualize that with just these formulas that you've been given, right? So that's why the tree diagram is really helpful. So what I'm going to do is I'm going to start this tree diagram here. And I know I have 3 race categories. So you can be white, or you can be Black, or you can be Asian, or nothing, I guess, in this situation. That's fine. We like to simplify problems. Okay, so now, right, notice that you could try to add up these conditional probabilities, but they're not going to add to 1, right? Because they're conditional on the branch they came down. However, the set of branches down here below each of the races, those have to add to 1. Okay. So now we can have a second set of branches, and I'll use a different color maybe, where they're either lactose intolerant, or we'll use the complement. They're not lactose intolerant. Sometimes you might want to use a different variable name here, but I just find that it's easier if we just talk about the complement in these cases. So we can be lactose intolerant or not. Lactose intolerant or not lactose intolerant. Okay. So on each of these branches, I can now attach a probability, right? And so there is a 0.82 probability of heading down that white branch. There's a 0.14 probability of heading down that Black branch, and a 0.04 probability of heading down the Asian branch. Then, given that I have already traveled down this white branch, so I'm here, right, at this crossroad here, then the probability of being lactose intolerant is 0.15. So 0.15, which means what? That this probability must be 1 minus 0.15. You're either lactose intolerant or you're not, right? And so 1 minus 0.15 is 0.85. Oops. Now we can go to the second kind of set of branches. So given that I've headed down the Black branch, the probability of landing on an L is 0.7. So here I am at the end of this Black branch. Now the probability of getting an L is 0.7, which means the probability of not being lactose intolerant must be 0.3, right? 1 minus. Same thing, assuming So we know I've headed down the Asian branch. The probability of then heading down the L branch is 0.9. 0.9, which means the probability of the not L branch must be 0.10. What we do when we want to figure out the probability at the end of each branch, what we do is we just multiply down the branch, because at the end of this branch, you're both white and lactose intolerant, right? So whenever you catch yourself saying and, you're going to be multiplying. Whenever you catch yourself saying or, you'll be adding. Okay. So we can find the probabilities of ending up at the end of each of these branches, right? And so what we can say is we can find these probabilities, and I'm just going to focus on this branch here. And there's a lot to write, so I can't really write it for each branch, but I'm going to put it on this fresh page here. So the probability of W and L, right? So using that intersection notation here is going to be, what do we know from conditional probabilities, right? So here I'm going to write, recall that the probability of A given B is the probability of A and B over the probability of B. That's a fact, right? Which means that I can rearrange this because I have a conditional probability and I have a plain probability. So I can rearrange this for the probability of A and B by multiplying the probability of B over to the left-hand side. Then I do a switcheroo, that's fine. And I'll bump it up so it stays on the same page. So the probability of A and B is the probability of A given B times the probability of B. The A's and the B's are generic, right? So you have to kind of keep them straight in your mind, because they could be, even though we have a B here, that B might not match this B here, right? So you have to really stay on top of things here. But if you remember that at the end of this branch, you're both white and lactose intolerant, right? So then the probability of being white and lactose intolerant is going to be the probability of being, we have lactose intolerant given white, right? We want to have kind of the same setup as the things that we know. Also, we haven't talked about the other way around, right? We could potentially change this entire question and say, oh, this percentage of the population is lactose intolerant. Of those people who are lactose intolerant, 14% are white, for example. So we could change it, but then it would change our entire tree and everything, right? So, but that's an option. So the probability of being lactose intolerant, given that they're white, then to match this setup here, I have to multiply it by the probability of just being white. So times the probability of W. Right. Notice that this W and this W, right, they have to match. So just make sure that you're using the right variables. Okay. Usually what I do is I cheat and I use some shorthand here. Instead of writing the probability of W and L, or maybe L and W if you want, they're the same, right? Usually I just end up writing WL. I know that's cheating, but it does help me see what's going on, right? So what you can do, just as like a quick visual, of all the possible outcomes that can happen, because remember, we're talking about all possible outcomes here. So at the end of each branch, you can write out the outcome. And I just use this shorthand notation, and I know that's lazy, but it's just to get an idea of the possible outcomes. So W and not L, BL, B and not L, AL, A and not L. Okay. So what you can do is you can find those probabilities by just multiplying down the branches. Okay. So we can find these probabilities by multiplying down the branches. Okay. So now if I talk about W and L, right, then I can find these probabilities, and I guess I should scoot this somewhere. Maybe I'll just copy it because I can paste. So that's going to be, you know what? Because I want to show that I'm multiplying down the branches, I'm actually going to reverse this order here. But that's the same. If A times B, does that equal B times A? Yes, it does, right? Multiplication, you can switch things around. So the probability of A, L given W. Okay, now I'm ready. 0.82 times 0.15. Uh, 0.82 times 0.15. I'm getting 0.123. And if you ever get something other than what I get, it's very possible that I slipped up and didn't punch it in correctly on my calculator. I don't have these pre-baked. Often I'll have these numbers pre-baked like Martha Stewart, and I just pull them out. Ah, here they are. But in this case, I do not. Okay, so then what I can say is I could put just the probability down here. Remember, the tree is just to help you solve problems. So even though there are proper ways of writing things, I usually just end up writing the probability at the end of each branch. So down below that first branch, I would write 0.123. Oh, there we go. So then I am going to get lazy here, and I'm not going to write out, we could write out the proper calculation for each branch. Seems like a lot of work for basically just running down the branch and multiplying those two values. And so what I'm going to do here is I'm going to try a different color here and say, okay, the W and not L, so they're white and not lactose intolerant, right? The probability of that happening is 0.82 times 0.85. So then 0.82 times 0.85, 0.82 times 0.85, 0.697. Okay, so that's for this one here. So now, let's see, I'm running out of colors here. I never go to this page. There's a fun color. So now what I'm going to do is I'm just going to put those values at the end of each branch, right? So 0.14 times 0.7 is, and I'm even going to do an equal sign. I know that's bad. Oh, so the reason that these don't add up to 1 is because now the entire range of outcomes is going to be all of these possible outcomes. Okay. And so what we're going to be checking eventually is that all of these branches add to 1, right? Because those are all the possible outcomes, or that we're assuming in this case, right? And so, but good catch, right? Because these two probabilities don't add to 1, right? But these probabilities, right? If you're white, then you're either lactose intolerant or you're not. Those have to add to 1. So it's a little bit tricky, right? But you're ahead of me. These end of the branches all have to add to 1, and we will check that. So, okay, 0.14. Oh, I fudged it on my calculator here. 0.14 times 0.7 is 0.098. Oh, I remember it was confession time. I just do BL equals 0.098. That's really bad, right? That's not proper. But it's just for me to solve this problem. So you can do whatever you want, I guess. Even weird stuff like that. I'll keep going with my weird notation because it works for me. 0.14 times 0.3. You can think about why I shouldn't write stuff like that. BL equals 0.098. It doesn't mean anything, but it does to me, right? And so that's those are little quirks that you can develop all on your own. Okay, so now let's finish these last two branches. So 0.04 times 0.9 means that 0.036, and then 0.04 times 0.1 is really small. And this calculator, it's always in scientific notation, so I have to bump my zeros. Okay, here we go. 0.004. Let me just check. 1, 2, 3. Okay. I'll know once I add them up if I did that incorrectly, because these have to add to 1, right? Oh, I'm in a different palette here. Okay. Always check that the sum of the branches equals 1. Okay. So what I'm going to do is I'm going to just write these out. So 0.123 plus 0.6, because I want you to see what I'm doing, plus 0.697, I think. 0.098, 0.042 plus 0.098, oops, plus 0.042 plus 0.036 plus 0.004. Scoot this over so I can show that they add to 1, hopefully. Okay, plus 0.036. I'm working backwards because I already had that one on the screen. 0.098 plus 0.697 plus 0.123, fingers crossed, 1. Okay, phew. Whee. Maybe a bright green. Whee. Love those check marks. Never have I been so happy to have something add to 1. Right? And so you just always don't want to double check, because if it doesn't, then you're missing an outcome, right? Or maybe you've done a calculation wrong if it's greater than 1. Then you want to go back and check, right? Because all our answers will rely on these probabilities that we found. Okay. You can find a lot of different, or you can answer a lot of different questions here. Okay. And so let's see here. what were some of the questions we wanted to answer? What percent of the entire population is lactose intolerant? So I'm just going to sneak this here. I'll bring it down here because now we're ready to answer this question. So what we'll see if we go up to our branches, and maybe because technology and whatever, I'm going to copy this. You can just use yours though, but I just don't want to have to be scrolling back and forth so much. And I am going to eliminate quite a few elements here. So I'm going to paste this and I'm going to remove this and say 0.123, remove that, 0.0697, 0.697, sorry. Just clean this up a little bit. Ta-da! Martha Stewart ready. Okay, so if I want to know what percent of the entire population is lactose intolerant, right? And so now it doesn't matter which branch I've headed down, but at the end of this branch, this first branch, I'm lactose intolerant. At the end of this third branch, I'm lactose intolerant. At the end of this fifth branch, I guess, we're lactose intolerant. So usually what I end up doing, especially if I'm working on, I don't know what happened there, on an iPad like this, and I can kind of make a mess and erase it, then what I'll do is usually I highlight the branches that I want, right? Or what's nice is if I have these little shorthands, right? Another way that I could do it is I could look for all the combinations that have an L and not the complement of L, right? So, or I could be saying something like, okay, this one, and this one. Those all have the L's, and those are all the possible outcomes that have the L. So I like to highlight because it kind of shows the different streams I could go, but really what you're doing is you're looking at all the different combinations that end up with an L. So here, I'm going to say that the probability of an L is going to be, and I'm going to use proper notation now. You don't have to because it's just for you to solve the problem, right? But it's nice to see it. So is the probability of W and L, I'll even use the intersection, right? Plus the probability of B and L, plus the probability of A and L. How do I know that I'm adding here? Remember, as soon as you say or, you're going to be adding, right? And so when you put little check marks by each of these three, right, you're lactose intolerant if you're white and lactose intolerant, or black and lactose intolerant, or Asian and lactose intolerant, right? So you're linking these with ands, right, down each branch, and that's why you multiply down each branch. But then when you can be white and lactose intolerant, or black and lactose intolerant, or Asian and lactose intolerant, that's when you link them with addition. Okay. So overall, to get the probability of just being lactose intolerant, right, we can add up these probabilities. And so we find that it's 0.123 plus 0.098 plus 0.036. Notice that a lot of work went into constructing this tree diagram and finding these probabilities at the end of each branch. But instead of just doing it piecewise and doing whatever just the bare minimum of what you need, I prefer to just label all my branches, find the probabilities at the end of each branch, and then I can just refer to that for the rest of my questions, right? And so now extracting these probabilities that I need is not bad, right? Okay, so if I add these up, 0.123 plus 0.098 plus 0.036 is 0.257. So that's the probability of just being lactose intolerant. Yeah. So now there was a second part. Let I catch up here. Now, the second question we want to answer . And maybe what I'll do is I'll try to keep it on the same page just by bumping this up just one line, and wish me luck. So what % of people who are lactose intolerant, thank you, are Asian? Okay. And so this is going to be, if they are lactose intolerant, what's the probability that they're Asian? So what we can do is we can rewrite this is what's the probability of A given L. Yeah, so the probabilities are going to be proportions, but proportions are probabilities. So those are interchangeable, and then we can multiply by 100 to get it to be a percentage. Nice. And also, looks like you guys got it. Nice. So good. Because I'm dealing with a page break and I so desperately want to keep it on one page, I am going to write across the page, and that's bad, but I'm okay with that. So that's the probability of being Asian and lactose intolerant over the probability of being lactose intolerant. Even if you didn't use the formula, right? Because taking this question and figuring out that what you need to find is the probability of A given L, that's difficult, right? But you could just take a step back and say, okay, of the people who are lactose intolerant, what percentage are Asian? Well, if they have to be lactose intolerant, then 0.036 of everyone are Asian and lactose intolerant over the total, which is 0.257. So you would have gotten there regardless, but this is technically the calculation that we're doing. So then that's going to be the 0.036 divided by 0.257. Luckily, and as is always the case, we found the probability of L in part A, so then we would rely on that here. If we hadn't, then you would have had to find that first, right? Exactly, good. So 0.036 divided by 0.257 is 0.140077821. So that's going to be roughly 14%. Nice. So these problems can be tricky, right? But you just kind of have to work slowly and methodically. And I do find that the tree diagram really helps, especially so the tree diagram is going to be useful as soon as you have kind of 2 consecutive events, right? Test 1, then the final exam, test 1 and test 2, those types of situations. You could even use a tree diagram if you have independent events, right? So if the probability doesn't depend on what happened before, you could still do that, right? Then the probabilities at the end of each branch would be the same, right? But then you're talking about the same events. But I think there is a question here. Yeah, here. So the other 2 problems, and I'll post the solutions to these, but I just want to talk about them. So Hacksaw's Boats of St. Lucia takes tourists on a daily dolphin/whale watching cruise. Their brochure claims an 80% chance of a sighting a dolphin or a whale, right? Or potentially both. Suppose that there's a 75% chance of seeing a dolphin and a 10% chance of seeing both a dolphin and a whale. So you've been given these different probabilities, right? I would probably start this with a Venn diagram. I think it's the easiest way to visualize this. You don't need to, right? But then we can find things like, what's the probability of seeing a whale on the cruise, right? Find the probability of seeing a whale, but not a dolphin. These are easiest to visualize with just a Venn diagram, right? You're going to have a dolphin circle and a whale circle, and then some overlap. So for question 3, it says the brochure claims an 80% chance of a sighting. Okay. You can assume the sightings from day to day are independent. Okay. That means that every day you go out, there's a 0.8 chance of seeing something, right, of a sighting, which means that there's a 20% or a 0.2 chance of no sighting, right? So you're going to have S and the complement of S. So then the first day would be the first layer. And then regardless of what happened on the first day, you might have had a sighting. Then you go out on your second day and you might have a sighting or might not have a sighting, right? Second day, or sorry, on the first day, maybe you didn't have a sighting. You go out again, they're independent. Oh, sorry, I just got a direct message here. I'll talk to you after class, okay? So you didn't have a sighting, and then you might have a sighting or you might not have a sighting, but the probability of a sighting is going to be 0.8 regardless of which tier you're in, because they're independent. So it's a little bit easier that way. Yeah. So we dealt with the hardest one together. Okay. Like, what time is it? I've got time. I've got time. You think you have time? Okay, so good. So what I wanted to talk about today, to start today, although I'm glad that we took some time to review that stuff, but today I wanted to, where is it? Post, and I did. Start talking about the distributions of random variables. Now, we're going to go a little bit deeper than I usually do. So this is just part 1. And then I'll post part 2, create new note. Okay. So what we're going to do is we're going to start talking about, let me just wait for it to catch up. Copy. So this is now, it's going to be, it's now called chapter 4, 4.1. But the content is the same. So what we're going to start talking about is distributions of random variables. So we've talked about variables, right? We know that that's all your columns in your data set, right? So each column is a variable. And because the outcome of each variable for each observation is random, we call them random variables. Okay. Usually we talk about X as some random variable, and then now we're going to talk about the distribution of X. Okay. So we're going to talk about the distribution. We've already seen for numerical data, we can look at the histogram, right? And we talked about the shape, the center, and the spread, right, of a normal distribution, for example. So we've already seen a normal distribution because we identified it as a shape that looks something like this. So something like a bell curve. That wasn't a very pretty one, was it? But that's okay. So we already know that if we see this shape, right, this normal distribution, then the best measures of center and spread are going to be the mean and the standard deviation. Okay, and so just to refresh some notation here, because it's been a while, right? Remember, X bar is the sample mean, mu is the population mean, right? S is the sample standard deviation, and then a lowercase sigma is the population standard deviation. Yeah. So what's fun is that regardless of the mean and the standard deviation, okay, the normal distribution is always going to be centered on the mean. Okay. So regardless of what the mean is, it's always going to be centered on the mean. And I'll show it by mu. And then I'm going to fit approximately 3 standard deviations of the on either side of the mean underneath the curve. So I'll do it like this. So here, if I go out mu plus sigma, mu plus 2 sigma, and then here mu plus 3 sigma. I can do the same thing on the other side. Mu minus sigma, mu minus 2 sigma, and I didn't do a very good job drawing this curve here. Mu minus 3 sigma. Okay, so what's going to happen is that regardless of what the mean and what the standard deviation are, that's always going to be true. And we use that, we leverage that fact, okay, in our analyses. So there is more room in the tails, and I'm going to bring in that list of little fun facts. So the little fun facts, LFFs, I like to call them. So just a couple of more things that we need to remember is that the tails of the normal distribution, they actually extend, they keep going to negative infinity and positive infinity. Okay. The area under the curve is a probability. Okay. And so that's how we're going to be calculating probabilities, is finding areas under the curve. Okay. And then the total area under the curve is 1. Now, if you're thinking total area under the curve, you might You might be in Calc 2 right now, and you're thinking, oh man, do I have to integrate this or what? No, you don't. We're going to skip that part, but that's what we would be doing, right? And so, yeah, yeah, so don't worry, we're not going to do that, not in this course. Okay, yeah, so, but that's what we would be doing, right? And so those tables that I posted have already done the integration for you. So we completely bypass that, skip it, but just know that that's what's been done, right? And so you could integrate to find the area underneath the curve. The total area under the curve is 1. Remember, it goes from negative infinity to positive infinity, so you technically have to integrate over that entire interval, and it's not an easy integration, so that's why we're skipping it. I wish the normal distribution was nicer to deal with, because it's so common, right? We'll see some where we could integrate it, but for now we're talking about the normal distribution because it's the most common distribution that we have to deal with. And so, yeah, the total area under the curve is 1. That's going to be really important to remember. Okay. Yeah, exactly. So you're taking limits in either direction. The normal distribution is symmetric about the mean, which we've already talked about, right? We've got the symmetry about the mean. We use the area under the curve to find or calculate probabilities, right? Usually we're not really calculating them, but we're finding them. So often these questions will ask you to find the probability, which means you have to find the area under the curve. Now, this is where it gets a little bit tricky, right? Because when we started the previous section, I said, okay, this is the section that I'm going to call probability, right? So those probabilities, though related to the ones that we're about to do here, that's not what I want when I ask you to find the probability. Okay, so in this case, it means to find the area under the curve. So I'll highlight that because that's a key difference, and it's not obvious in the beginning, right? We talked about probabilities, we just figured out how to do probabilities, but now we're saying that the area under the curve is a probability, and it is. Yeah. So one thing that's kind of nice is that we have quick approximations for the areas under the curve. These aren't the rules that we're going to stick to, okay, but they are nice to introduce. Because remember, we said that, okay, we can move out 3 standard deviations from the mean, right? And so at those cutoff points, we have specific areas between those 2 points. So we have some building blocks for finding areas under the curve, which is really saying for finding probabilities, right? And in this case, because these are approximations, approximate probabilities, but it does give us some intuition about probabilities of certain outcomes. Okay, and I've tried so many different times to draw this, and when I went to program it, it was even harder than drawing it by hand, but here it is. So it's called the empirical rule, but I usually just call it the 68, 95, 99.7 rule because that's the most telling of what's going on. So I just call it this, but technically it's called the empirical rule. But I think if you Google it, if you Google the 68, 95, 99.7 rule, it'll just come up with a bunch of answers, right? And so it's pretty common to call it that. So what it means is that if we'd centered on if we let the mean, yeah, you will 68, 95, 99.7, 68, 95, 99.7. You got it. You can do it. It's worth it. Yeah. Hey, you forgot the 95. That one's easy. You can forget that one. Yeah. And the 95 is going to be a key player for us. So, but we'll get there. So if we let the mean be 0, right, then if we have cutoff points at 1, 2, and 3, what does that mean? It means we have a standard deviation of 1, right? This is what we call the standard normal, but here I'm going to let sigma be 1. Then this cutoff point is at 1. This cutoff point is at 3. This is at -1. Whoops. -2 and -3. It's nice when you have a little bit to go off of. When I try to draw it, it just makes a mess. So here, the 68, what's that saying? It means that 68% of the curve, or 0.68, is the probability of being within 1 standard deviation of the mean, right? On the negative side and on the positive side. So it's that central 68% of the curve. Then we can move out to 2 standard deviations away from the mean. Now we've captured the central 95%. Okay. Then if I go to 3 standard deviations beyond the mean, then I've covered the central 99.7%. Okay. So what we can do is we can use these areas and we can use them as puzzle pieces, right? And so that's kind of fun. And with some practice, right, you'll get really quick at figuring out these puzzle pieces. And so if you have an observation that is, and let me just see, I don't think I have an example. I do. It's almost like I've taught this before. And I use the same setup. My brain works the same time, or the same way every time. It's weird, guys, but it's true. So it's like it echoes in here. We can use these properties to find other probabilities, such as the areas in the tails or between the 2 values. So the trick is to think of each piece as a puzzle piece. So what if I want to find the probability of seeing something less than mu minus 2 sigma? So what you can do, right, is remember the 68, 95, 99.7 rule. Okay. And what I do is I draw this out. There's no right or wrong way to get there. And I encourage you to really think about how your brain works here, right? If your brain approaches this in a different way than I do, that's totally fine, as long as we end up at the same answer, right? And so I'm not saying that my way is the best way or even the most efficient way. I know how my brain works. And so try this kind of on your own later and see how it works for you. Okay. So how my brain works is like this. So if I've got mu here, and the one that I'm interested in is, oh yeah, so one option is 1/2 minus 0.0228. That's not how my brain works, but it's really good, right? So we're going to end up at the same answer, but no, that's way too complicated for my brain. I can't do that. So how my brain works is I know that if I'm interested in mu minus 2 sigma, Yeah, that is why teaching math is difficult, because we all have these different processes. So this is the point that I'm interested in. But if I want to find the probability, remember the probability is the area under the curve that corresponds to being less than mu minus 2 sigma. The area that I want is this area that is less than mu minus 2 sigma. However you want to get there is fine. Some key things to remember is that the total area is 1, right? And so recall the total area is 1. But also remember, even more confusingly, that these tails technically go to negative infinity and positive infinity, and they never actually close on the axes. That's weird, right? That's kind of mind-blowing if you think about, okay, the total area is still 1 somehow. Yeah, so the total area is still 1, but the curves, the normal distribution never really closes. Why is that? If we think about what the area under the curve is, it's a probability. It's just making room for there is a probability of something happening. Okay, and so here, if I want to go back to the problem that we're solving, and I know that mu minus 2 sigma is a cutoff, B cutoff that I'm interested in, then one thing I could do is I could go to mu plus 2 sigma. And what do I know from the 68, 95, 99.7 rule? I know that this area here is 0.95 because I have moved out 2 standard deviations on either side of the mean. Now, I also know that the total area is 1. Okay, it's symmetric about the mean. Okay, which means that the area in this tail on the right side has to be the same size as the area in the tail. That's the one that I'm interested in, right? And so I've got 0.05 left over, but I have to split that evenly amongst the tails. So here, this area and this area, this is 0.05 divided by 2, which is 0.025. Okay. And then this area is also 0.05 divided by 2, which is 0.025. So what you could do is you could go through each of these, right? We know the area in between, and so if it helps you, you could find each of the areas in the tails, right? Remembering to split up that remaining area evenly amongst the tails, right? So for example, if we're talking about the area in the tails from -1 and +1 out to their respective infinities, then we would have 1 minus 0.68 left over for the tails. So 1 minus 0.68 is 0.32, which I would have to divide evenly amongst the tails. So divided by 2. So I have 0.16 in each of those tails. Okay. So from here, from -1 down to negative infinity, I've got an area of 0.16. And from +1 up to positive infinity, I've got an area of 0.16 as well. Okay, so you could go through and you could chop up this graph as much as you want. What if you want to find the area between mu minus 2 sigma and mu plus 3 sigma? Okay, so here we go. And again, just think about how your brain approaches this. I think the easiest way to do this is to draw out the curve. Now, I know in the beginning when we're drawing these curves, they don't Oh yeah, they don't make sense, right? That's okay. They're going to make sense the more we use them. So here, if I draw out the normal distribution, and here I am at mu, so some generic mu. If you want to, you can let mu be 0 and sigma be 1, just to simplify things, but I'm going to keep it kind of generic here. So between mu minus 2 sigma and mu plus 3 sigma. So here, from mu minus 2 sigma up to mu plus 3 sigma, the area that I want is the probability of being between these two values, right? Between the lower cutoff and the upper cutoff. So the area that I'm interested in here is going to be this area here. There are lots of ways that we could solve this, right? A few ways come to mind, but for me, I have a particular way that I want to show you. It's not necessarily the way that my mind would work. I would probably find the area in both of these tails that I don't want and subtract them from 1, right? And then I'm left with the area that I want. Instead, I want to show you another method, and that is saying, okay, well, I know the area from the mean splits it in half, right? So the area from mu must be 0.5, okay? Probably, I don't know, we'll see. We'll let you check. So here, right, if I want, let's see here. If I want this area, well, that's going to be 0.5. And this area is going to be 0.5. What we can do is we can think about, okay, if I've moved out 2 sigma, so 2 standard deviations, then I could go to here and say mu plus 2 sigma has an area in between here of 0.95. Okay, I could use that. So one option is I could use that to find this area, right, which we already decided was 0.025, which I could subtract from 1, and then I would have to subtract this from 1. What I'm going to do instead is I'm going to say, well, 0.95, I can split it in 2. Okay, and so here, 0.95 divided by 2 is, let's see here, 0.95 divided by 2 is 0.475. Okay. Which means that this chunk between mu minus 2 sigma and mu is worth 0.475. Okay. Whereas here, if I'm talking about this chunk that I'm interested in, right, I could do the same thing, and I could say from mu plus 3 sigma down to mu minus 3 sigma. And now I'm going to go like this. I know this area between these two is 0.997 approximately, which means that this area from the mean to mu plus 3 sigma must be 0.997 divided by 2, which I think someone put in the chat a long time ago, but that's okay. We're getting there together, 0.4985. I am impressed that you guys are so on it. Okay. So then what we're saying is that this piece, this half a piece, is 0.4985. And you know what? Maybe undo. I'm going to use a different color here because this was worth 0.475. So then the area that I want is the sum of those two. So then I can say 0.475 plus 0.4985. 0.475 plus 0.4985 is 0.9735. Unless I did that, unless I flubbed it, but I'm feeling pretty good, but there's a chance that I didn't do it right. But that's the answer that I'm getting. So maybe just see if that's what you're gonna get, right? And there are lots of ways that you can break up these puzzle pieces and approach it, right? And so this isn't the one way. I just wanted to show you that you can leverage the fact that the mean splits the data in half, okay? Oh, hey, pretty good timing. Okay, there was another thing I wanted to say. Oh yeah, last thing we can check, right? Just as a check-in point, this area from mu to mu plus 3 sigma, it has to be larger, right? Yeah, plug it in, plug it in, plug it in. So 0.4985, that has to be larger than 0.475, right? If you're finding that this area that's larger has a lower probability, then that's bad, right? Something happened. But it checks out. 0.475 is less than 0.4985, so I'm okay with what I've done here. Okay, I think I'm out of time, and my iPad is dying, so we'll leave it at that. If you have any questions, let me know. Otherwise, I'm gonna stop this recording. I'll see you next day.